12:31. And let's do 121 question. And to do that, I think I've got to change the share settings probably, so you can show me, or you can describe it.
I probably have to show you the actual question.
Okay. Yeah, so let's do that. Did I? Oh no, did I mess up? I think I logged in too quickly on my desktop. I think I'm host on my desktop. How do I tell?
It says one is host and one is co-host, and co-host can usually do the same things host can.
Oh, okay, so maybe I don't need to worry about it. But I can't seem to turn off the sharing. Well, let me go to my laptop. Let's see how far I can get with this.
Looks like your co-host is the one recording. I don't know which one's your co-host, though.
Oh. Yeah, that's my desktop. Yeah. Huh. Who can share one at a time, all participants?
Okay, I can share now.
Okay. Yeah, something's weird, but I'm not going to worry about it as long as we can still go forward. All right, yeah, share your screen with me. Let me see if I can comprehend this problem. All right, this says I wonder if I should take a picture of it. You know what I do? I might do a screen grab. Might be a good way. Nice. Okay, then so what if I paste it somewhere? Let's see. Well, Microsoft Word might just be a good place. And then that way I can read it and then have my camera on at the same time. This looks like it's a long worded problem. Let's see if I do paste. Does it show up? Oh, nice. Nice, it does here. Okay, so with that in mind, before I even read it, let's see if I can come back to Zoom and do two things. Number one, this will bump you off, and I think that'll be okay. I'm going to go to sharing my screen, which should put it back up there, Microsoft Word. Okay, good. And then maybe I would be better off to not do that. Maybe I'd be better off to share my camera. Let's do that. Then I can just read it. Share. Okay, we're share. iPhone share. Readjust. Oh, that looks good. Right. Connect screen sharing, Bluetooth. Okay, and then on this one, I'll go back to the Word so I can see what's going on. Nice. Okay. All right, so this is from Physics 121. And this one says, do not discuss
last week's quiz.
Oh, okay. Yeah, I was going to say, whoa, it says do not discuss. Okay, so this is last week's quiz. All right. So good. I'm glad going back and kind of looking at this. This says for number one, a 200, and it's got a picture that kind of looks like this. And it looks like it's saying here a 200-kilogram roller coaster shown at the right starts at rest. So I'm going to put initial speed equals to 0 from a height of 17 meters. So I'm going to put a little 17 meters right here. 17 meters above the ground. Turn off these crazy notifications. Stop. I'm like, turn those things off. 17 meters above the ground. The vertical loop, so the roller coaster goes around in a vertical loop, okay. A vertical loop of radius 4 meters. So here's a 4 meters. At the top of the loop, the normal force exerted by the track. Now they don't really, oh good, the picture shows which way. So when the roller coaster gets right here, and so I don't get too crowded, I'm going to put normal force of 1,400 newtons. Calculate the negative work done by friction and by air resistance between the start and the stop of the loop. Now, wait. Oh, top of the loop, not stop. Top of the loop. Okay, good. Now, I've done a number of these, and I don't know if I helped you or not before, but these really break into two pieces. One is the energy that is more recent than, and I think that's what you're doing now, the energy, and the other half of this is the centripetal force. Let me do that one first. And so one thing we learned back with Newton's second law, I believe it was chapter 6 of your book, is that Newton's law says if you add up all the forces, that has to equal to ma. So if we do a free body diagram, when the roller coaster is up at the top of the loop, we will have pulling it down is gravity, and also pulling it down or pushing it down is maybe a better way of describing it, is this normal force. And both of those are going down. So when you add up all the forces, we're really talking only about the vertical direction. So I'll put an mg and an n. And here you have a judgment call to make. Do you want to call down positive or do you want to call it negative? The traditional way is to call down negative, but since everything is down and it's kind of just nicer to mess with positive numbers, I'm going to say let's make a grid where down is positive. So I have a positive mg and a positive normal force, and that has to equal then to mv squared over r. That is, again, the part from the circular motion of chapter 6. That's the part that's saying if you're going in a circle, you are accelerating. In fact, maybe I should have wrote first ma, where then a is v squared over r. So those two together, the weight and the normal force, is what is making it turn. And the problem was somewhat easier because they put us at the very top of the loop. And so we only have to add up forces in the y direction. The x direction is just kind of boring. I suppose there could be a frictional force, and then that would just equal to how the speed changes with time. But that's diverting from anything important, and that's not relevant for this. That's just saying, hey, the roller coaster is slowing down at the top because of friction. It's not slowing down because of gravity. Whereas if the roller coaster was somewhere else other than the top, a component of gravity would be slowing it down or speeding it up, depending on whether it was before the top of the loop or after the loop. Okay, so knowing this, we can put in some numbers here before we even get to the energy issue. The mass is 200, G is 9.8, the normal force is 1400, the mass again is the 200, the radius is 4, and so the unknown in the equation thus far is the velocity. And so I, of course, haven't even got to the energy part of it yet, but let me go ahead and then do a quick calculation. So 200 times 9.8 plus 1400, okay. Then I'll move the 4 over, so times 4, then divide that by 200, and then taking the square root of all of this, we're looking at a speed of about 8.20 meters per second. And so that's kind of the first thing that goes off in my head. What is the, what information can I get from just knowing it goes in a circle and using forces and Newton's second law, albeit a couple of chapters ago. And so that's the first piece of information I get. So let me call that page 1 and then go to page 2, because the second thing I would do is to say, well, this is really a question about energy, because it says calculate the work done by friction and air resistance, which are always opposite to the direction they move. So it's always going to be negative work. So the author here helps you out and says, the negative work. But it says this, that the energy you start with, and there's different ways of writing this, is equal to the energy you end with. And let me give you both here for a second, Jonah, because last week when I was talking, and I think it was with Ryland, that your professor does it slightly different, but it's the same thing. I like to write it this way, that if I write in all the energies, and so there would be gravitational potential energy, there would be kinetic energy, that goes where? Well, after the roller coaster moves, it might have a new gravitational potential energy. It might have a new kinetic energy. And it might have done some rubbing, so there might be some heat that is formed. That is, the energy went to form heat. Now, you could write it the same way with the heat on the other side of the equation. You might then say it a little different. You might say, well, this is the energy I start with, and then you take away some heat energy. You take away some non-conservative work. And that's what this question is about, that term. And then this is what you're left with. This is the mechanical energy you are left with. So whichever way you want to look at it, that heat is the end product of some energy that came from the beginning energy. Or if you want to look at it, the ending energy is less than the beginning energy by the energy that was taken away by the non-conservative force. You're really saying the same thing. And so in this problem, you're really saying find that heat energy. That is the work done by a non-conservative force, which in this case is friction and air resistance. So the two resistances together would fit right here. So I don't know which way you would prefer. Unless you want to speak up, I'll go with kind of the way I'm kind of normally like it and used to it. And so I'll say, okay, let's take the energy we start with. So the roller coaster has a mass of 200. G is 9.8. And back to our description here, it's 17 meters above the ground. Also, it says it started from rest. So that would tell me the total energy I start with. Now, the other side of the equation now is what energies does it have at the top of the loop? And at the top of the loop, I would say it has a height now of 8 meters, because coming back to the loop, the radius being 4 meters, it's 8 meters above the ground here. So the gravitational potential energy would have a height of 8. And of course, it is moving at a speed of, and that's what we were getting from this, what I'll call our first step of here at speed. So this is the 8.2 meters per second squared. Oh, I ran out of room on my paper, so I'll just put plus heat down there. So if I grab my calculator, I would say, okay, I started with this much energy, 200 times 9.8 times 17. So this is 33,320 joules. Now, when it gets to the top of the loop, it has this much energy because of gravitational potential, 15,680 joules. It also has this much because of kinetic, 1/2 200 8.2 squared, 6,724. So the fact that, these don't add up to that means that that rest went into heat. And so coming up here and grabbing the 13,000 and subtracting the 15,000 and subtracting the 6,700 and hit enter, tells me that 10,916 joules was dissipated as heat, which you can again say it either way. You could say it was the non-conservative energy that was lost, or it's the heat energy that was formed, so that all of your energies at the end add up to what you begin with. Now, that's calculate the so that's number 1 on the quiz. Were you asking about number 2 also?
I was asking about number 2 also, but I'm glad. I think I got the same answer for number 1, so that makes me feel better about that.
Oh, good. Okay, good. Yeah, so you did this quiz and you probably don't know the results quite yet or something.
No, I don't.
Yeah. Okay. So good. So I'll move on to number 2 here on the quiz. And so let's see, number 2, it says you have and I'll just kind of draw a picture while I'm reading it here. You've got this block kind of on this incline, okay? And it says it is a 4-kilogram block, and it is on a frictionless ramp that is tilted at an angle of 25 degrees, and it is attached to a spring. Here's the spring, and the spring has a spring constant of 20 newtons per meter. Well, good. And so that's one thing that was not in number 1. We did energy, but it did not involve any elastic energy. So this one, we get to do that. Initially, the spring is at its equilibrium length, and the block is released from rest. I'm going to pause for a second. I think that would be worded better if the spring was at its natural length. But maybe I'm being too anal there, because I read equilibrium as a balance between the spring and gravity, so it's already balanced. If I let it go, it won't move. So I'm quite sure that is not what the author means here. The author means the spring's at its natural length, and it's got to stretch a little bit to become into its equilibrium with gravity. And in fact, this one would go past the equilibrium because it would build up so much speed, it would eventually get to equilibrium and then go past that. And that might even be the challenging part of this. Well, anyways, the problem then says, calculate the kinetic energy of the block when it has moved a distance x. So express your answer as a function of x. Okay, so this is one where we don't get a concrete number, but we get a variable x, which probably means we're going to need that in part B. But I'll wait to read part B when I get there. Okay, so I'm going to do the same thing. I'm going to say initial energy is equal to final energy. And on the beginning part, I'll say there is an initial gravitational potential energy. There is an initial kinetic energy. And what I didn't include in the last problem was the initial elastic energy of the spring. So that one needs to be included this time. Now, after it moves, it would have a final potential energy, which is going to be a little bit less because it's going downhill. And then it's going to have a final kinetic energy, which could be more or less. At first, it would be more, but eventually the spring would stretch enough that it would be slowing it down. So this number could be bigger or smaller than, oh, well, wait, that was 0. So I guess it can never be smaller than that one, but it could speed up for a while, then slow down. And then, of course, we have the elastic energy of the spring. And maybe just for completeness, I'll turn my paper on its side and say plus any friction or any heat. But this problem made it very, very clear at the beginning that there was no friction to worry about. So I can cancel that off. It also made it very clear that it starts from rests. So that number would be 0. And as I said, I think it would read better if it had said the spring started at its natural length. It makes me wonder if it's equilibrium with no mass on it or equilibrium with the mass on there. But like I said, if it was already at its equilibrium and with gravity, once you released it, nothing would happen. So I'm pretty sure they're saying that the spring is unstretched. So an x initial would be 0. And just maybe to remind you, if you don't already know, the x in this equation is a measurement of how far the spring is stretched from its natural length. So all of that is to simply say here that we have the beginning part of this as mgy initial. Now, they don't really even say or indicate what that value is, but that's okay. That's part of maybe the interesting part of this equation. Now, the other side of this is to say we have an mgy final, and then there is some speed that it's going to have, as well as a distance that it stretches. So let's do this. Let me go ahead, come back to my picture, and call x kind of this down the incline, because x really is how far this spring stretches. So coming back to our equation, I already argued then that it's going to start at x equals to a 0 position. And if it moved down, say 1 meter, then the final position would be 1 meter. So that's the x that they're talking about, where they say, find an expression as a function of x, okay? And they're after this whole expression here, because it says calculate the kinetic energy of the block when it has moved a distance of x. So if I were to rewrite this, I would leave the kinetic energy by itself. In fact, I might even just put kinetic energy. That's what I'm trying to solve for. And then over here, I would have this mgy initial minus an mgy final minus a1 half k. And I'll just write it as x squared. I won't necessarily call it a final x. That's just however far it's stretched. Okay, so this would be my expression. Now, clearly, again, coming back to the picture, I'm hoping you can see that what the vertical height is as this thing moves down would depend upon how far x is. And so I can make a little triangle. Maybe I'll make it in a green color here. But if it started here, y initial, and came down to this point, y final, then what I would call this is y initial minus y final. That's this height of it. And then this is the x. And then, of course, this angle is 25 degrees. And so what I'm trying to say here is that the sine of 25 degrees would be the opposite. That would be y initial minus y final over the x. Now, if I move the x to the other side and keep this in mind, that the difference between y initial and y final is x times the sine of 25, I can then use that over here in this equation, because this would be mg, when I factor out each of them in mg, this is y initial minus y final minus the elastic energy. And that right there can be replaced with x sine of 25 degrees. And so I would say that I have an equation, although maybe I could put some numbers in now, because they say the mass, what do they say, is 4. So that's a 4. That's a 9.8. That's an x. Sine of 25, I'll just grab my calculator here, or check the mode. Good, I'm in degrees. So sine of 25 would be 0.423 minus 1/2, and the k they said was a 20. And so that equals, sorry about that, kinetic energy. And so maybe grabbing the calculator and saying, okay, there's the sine. If I multiply that by 4 and that 9.8, I've got 16.6x minus 10x squared is the mathematical equation for the kinetic energy. I hope that's what you got on the quiz.
I think so. I think so. But your
Okay.
method was different for sure.
Yeah. Okay. Okay. Now, then extending this to part B, it says calculate the maximum kinetic energy of the block as it slides down and express your answer as a number of joules. A couple ways we can do this. I suppose the first thing that pops into my mind is really more calculus. In fact, I would maybe just put a graph here. If I'm plotting kinetic energy as a function of x, it looks like what I have is, since it's x squared, it's a parabola. It's negative, so it's an upside down parabola. But because it has a linear term here, it's off shifted. That is, when x is small, if you will, when x is equal to 0 even, you can see that we're going to get 0 kinetic energy. But it's going to increase because it's going to be more dominated by a linear function at first and then get overwhelmed by a quadratic function. So it's going to look like that. And if you had negative x's, you could do that. But anyways, there is the kinetic energy. So that would tell me, let's find the maximum of this by saying, how does the kinetic energy change with position? So if I take the derivative, I get 16.6 minus, and the derivative of this would be 2 times 10, which would be 20x. And that's the derivative. And we know we find maximums and minimums for that matter, but this is a maximum when we set that slope equal to 0. So 16.6 equals 20x, or 16.6 over 20 is the location. So 16.6 divided by 20 gives me a 0.83 meters. So that's the location where it is its maximum. Now I can use that and put it into this equation to then calculate what is that maximum. So 16.6 times my last answer minus 20 times my last answer squared. And my kinetic energy maximum is 6.90 joules. Yay. Hope I did those right.
I got very, very close to that number.
Yeah.
I got 6.86. So I don't know what the difference would be, but it's
Yeah.
very close.
Yeah, that just sounds like rounding, like, because I did 16.6, and obviously there were more decimals here. So,
Oh, yeah, that's probably it. Okay, well, thank you for going over them.
Yeah, my pleasure. That was a good one. All right. Nice. Okay, let's see. Did I write that one down? Let me write down number 1 and number 2 from quiz. So when anybody wants to see these, they can kind of scan that. All right, so let's see. Second on the list, it looks like we're Danny or Daniel, whatever you go by here, and number 3, huh?
Well,
Did you say, well, no, you already finished it, or?
no, I said hello.
Oh, hello. Okay, yes, hello. Okay, so good. Glad you're here. And so I'm going to put 122, chapter 30, number 3. I'll put a time stamp of about 104 and say, all right, chapter 30. Chapter 30, number 3. Oh, by the way, let me just say, anybody out there who has a question, throw it in the chat. I have 4 questions from earlier on that I'm going through. That was 1. I'm going to go through 3 more, but whoever has something else next, throw that up in the chat, and you'll be the 5th one here. Okay. So number 3, I'm going to have to go and read. Number 3 says, a conductor in the shape of a square loop. Okay, so here is kind of a square loop with edges that have a length of 0.4 meters, carries a current of 10 amps as shown. Now they point this way, so I equals 10 amps. Switch this one over. Okay, good. All right, so 10 amps as shown in the figure. Calculate the magnitude and direction of the magnetic field at the center of the square. All right, I'm going to start with direction. This is always an important process to learn, that we have these right-hand rules. I'm going to put my right hand in the screen, but I also want to point out, let me switch back to Zoom on this one too, so I can see it as you guys see it. Okay, that it's very easy to mix up your right-hand rules. So just as a quick review, You learned back in 121, the one called a right-hand rule for vector cross products. That is, you put your finger in the direction of the first vector, you adjust your palm so that you can then close your fingers towards the second one, and whatever direction your thumb is pointing is the direction of the cross product.
Mhm.
Right? So we have seen many cross products this semester and last semester. Kind of the first one that comes to my mind that you saw first last semester was R cross F. So that's why you were using your right-hand rule to do vector cross products when you were doing torques. A second one you saw last semester was angular momentum, which was R cross P. And so again, we would put our fingers in the direction of R, we would close our fingers towards P, and our thumb would give us the direction of the angular momentum. So that was a cross product. Now, this semester, we've seen a cross product for the torque in a magnetic field. So we saw mu cross B. And so again, you would put your fingers in the direction of the magnetic moment and you would close towards B. What else have we seen? In BIPs of art, we have seen the S cross R hat. Let's see, there must be an R squared, mu, an I.
Is there a 4 pi on the bottom of that UI?
Yeah, that's what I'm, oh, thank you. Yeah, I was thinking there was something more here. 4 pi, yeah. Okay, thank you. Okay. So again, we could do a right-hand rule. So all of these are done with the same right-hand rule, okay? However, there is another right-hand rule, okay? And it is the connection between currents and magnetic field. And it's not a cross product. Now, it was figured out as a convenient way from cross products. I'll give you that. But this is the one I'm going to use and try to clarify. You still use your right hand, and I think that's why it can confuse students. But it's not taking your fingers and closing them towards your palm. You're not doing this kind of motion. You're actually starting with the thumbs up shape, and you hold it there. You never move your fingers and you never move your thumb. And you do this. One of these is going to represent the current and the other one's going to represent the field. So if you have currents that are in a straight line, well, which looks like a straight line, your thumb or your fingers? Hopefully your thumb. So put your thumb in the direction of the current and your fingers will show you the wrapping direction of the field. So that's why I say current would lead to field.
Okay.
However, there's another way we do this, because sometimes we have currents that are not straight lines. Now, for this problem, we do have currents for a straight line, but sometimes we don't have straight lines. Sometimes we have currents in a circle. So if that's the case, use your fingers for the current.
Okay.
And then your thumb will give you the field.
So if it's like a ring or something, we would use our fingers to follow the current.
Right.
And if it's a straight line, you use your finger or your thumb. Okay.
Right, right. So I wish it was easy that I could say your thumb is always the current, but it's not. You got to look at what picture you have. And so things that have straight lines, your thumb will be the current and your fingers will be the field.
Okay.
Things where the wires are coiled up, like you said, a loop, you would use your fingers for the current and your thumb would give you the field. Now for this problem, you can see we don't have coils, we have straight lines, 4 of them in particular. But let me just call this one on the left, number 1. And let me just focus my attention on that one first. So I would use this right-hand rule. Sometimes I refer to it as right-hand rule number 2. so that you don't confuse it with the first one you learned, which is doing a cross product. That would be the one you would use for any of these 4 equations because you're doing a cross product. But for this one is number 2, and it's the way to find the direction of the magnetic field from the current. And so the first thing you got to decide here is, do I have currents that are straight lines, or do I have currents that are in loops? And clearly they're straight lines. So in this case, my thumb would be the current. And my fingers then would represent the field. And so if I grab my green pen to kind of represent the field, and you kind of imagine my thumb as this wire right here, then my fingers would be wrapping around this wire. So that means in the plane of the paper and to the left, my fingers would be curling outward. So I'm going to put what we try to represent a magnetic field coming out of the paper towards the video screen with dots.
Aren't we trying to find the magnetic field in the center of the box?
Oh, yeah, yes, we are. So thank you. So I just pointed that out, but you're right. I don't care about that. I care about in the center of the square. So if I watch my fingers curl around, they then point inward. So I would say, at least from this wire, the field is inward. Now, why don't we go ahead and look at the top wire? Let me call it wire number 2 with the current going this way. And again, imagine grabbing it with your right hand with your thumb in the direction of the current. And as you look at your fingers curling around, at the center of the square, they would be going in. So both of these go in. So these two together are definitely going to be in. And if you look at the third wire, so let me call this one on the right, the third wire, I grab my right hand and I hold it with the current, or my thumb in the direction of the current, and I look at my fingers, again, at the center of the square, my fingers are going in. So this would also be an in. And the same thing happens with wire number 4. Wire number 4 would be going in. So every wire, 1, 2, 3, and 4, the 4 sides of this square are all going in. So that means when I add them all together, I'm going to get in. So the first answer is in, or if you want to put negative k hat, inward. And so that's, I'll call it the first half of the problem. What direction is the magnetic field? And so this is inward. Okay, so now I can go on and do a calculation. And so why don't I start with just saying, okay, what is the magnetic field from wire number 1? Now, let me not repeat what I got in the lecture by doing this integral, but we came up with an equation that looks like this in the lecture, and also it's in the survey book. I made a solution trying to clarify this last night, and I don't know if you got a chance to see it yet, but it made me think about it while I was doing the solution, and I wonder what the OpenStax book, and I thought I looked pretty good, but I'm going to give myself a little bit of a doubt here. I did not even see the author derive this in the OpenStax. I was disappointed. He only did an infinitely long one.
He did it for like one line and then said, we're going to look at infinite, and ditched it.
So did he ever come up with this equation?
For like one line,
Oh,
I think.
okay. So maybe it's there because yeah, I couldn't see it. All I saw was him start off with the bits of art, and then he went to the infinite long wire, and I thought, whoa, wait a minute. What about wires that are not infinite? Anyways, let me emphasize that this is an important thing to know, that you should know why wires that are infinite, which is kind of a subset of this one, but it's an important subset. So if it's infinite, I'll just put here, it's mu naught I over 2 pi r. That's what this equation becomes when you put in 90 degrees here and negative 90 degrees here.
No, I was looking at a different solution. He doesn't even do that.
Okay. So let me kind of quickly run through the solution and encourage you to look at section 1 of the Survey book or the video lecture, because I did this. I said, let's take a wire that maybe the current starts here and ends here. So the current goes left to right. And let's pick some random point P. And to mark things off, let's draw a line perpendicular to the point P. And then if you make an angle that is between an angle that involves 2 lines from P to the beginning of the wire and P to the perpendicular crossing of it, that is called theta 1. And then the same thing, if you draw a set of 2 lines, again, one of them being from P perpendicular to the wire, and the other one from P to the end of the wire, that's theta 2. That's the definition of theta 1 and theta 2. And then the A is the distance away. I is the current in it. There is one little confusing subtlety here. He says when you make an angle like theta 1 that swings clockwise, you get greater than 0. So that's your positive angle. So something going clockwise is greater than 0. And that's not normal. And if you swing it counterclockwise, that's less than 0. And so let me emphasize again, I'm trying to remember what problem I sent out last night, but I did some extra talking about this, and I would encourage you to watch that video, the whole 45 minutes of it, because I tried to explain that, because that was the question I got. Somebody was having troubles trying to understand. Oh, that was Chase, huh? Who was trying to decipher here between these angles and what they meant by them. I think that was you, Chase, but
Yep.
Somebody did. And so I go, okay, I'll just spend an extra long time talking about this equation and what those angles mean. So that's why I'm taking a little extra time right now. And so without deriving this equation again, let me use it for wire number 1. Okay, so I'm going to take this first page, put it off to the side, and get a page number 2 going here and say, all right, let me apply this equation. I'll just repeat the equation to get us started on page 2. Now, I might need to come back to this picture, but to make this current look like this one down here, you might have to say, well, let's turn it so that the current is horizontal. Okay, but sadly, when I turn it like I just did,
It's still going the wrong direction, right?
go in the wrong direction. All right, so let's do this. Let's turn it and flip it over. So there is the center of it. There would be the two lines to the end of the wire. And there would be the perpendicular. So that would be theta 1 and that would be theta 2. Now, the good news is if you get the current going the wrong direction, you end up getting theta 1 and theta 2 backwards, which means you get a minus sign. But to be quite honest, I'm just going to calculate the magnitude of B. So if you get it backwards, you get a negative B. And then if you ignore the negative, at least you got the magnitude and we can get the direction already. And that's what we already did is the direction. So I'm not even really interested in direction. I'm just interested in magnitude. So because of that, part of me wants to say, hey, let's just leave it here with the current going in the wrong direction and I'll get a negative. But to be a little more accurate, I could flip it over and there's my point P, the center of the square. So here's the square, if you can kind of see through my yellow paper here. And then this is the theta 1 and the theta 2. So when I flip this back over, this over here is actually the theta 1, and this over here is actually the theta 2. See how they're backwards now that the current goes the other direction.
Okay.
But I'll say it again, that's really not really important because even if you mess up with theta 1 and theta 2, like I said, they're each 45 degrees. I didn't draw my square very good, but maybe if I try to draw a more accurate square. You know, when you make a diagonal across it, you know, that right there is 90 degrees and perpendicular down the middle is 45. So I would say theta 1 and theta 2 are each 45. However, here's where you really have to be careful. And then you can see it better when I flip it over. Remember our definition of theta. So theta 1 is a positive 45. So theta 1 is a positive 45 degrees. But theta 2 is a negative 45 degrees. One has to be positive and one has to be negative. One goes clockwise and the other goes counterclockwise. If you get them backwards, you're still okay as long as you label one as positive and one as negative. But if you label them both as positive, now you're messed up because you would have sine of 45 minus sine of 45 and you'd say 0 magnetic field. So knowing the definition of the angles is important there. All right, well, let me flip it over and, oh, it froze. Let me stop sharing and reconnect, see if that'll fix it. See what happens here. All right, now we're back again. Okay, so putting in the numbers for this problem, the mu naught is the 4 pi times 10 to the negative 7. Good. The current, they said, was 10 amps. Downstairs here, I'm going to put the 4 pi. Let me bring my picture back into play here. They said the length of the square was 0.4, so the distance to the center must be 0.2 meters. And so that was the meaning of the A there. And then I have the sine of 45 degrees minus the sine of a negative 45 degrees, which we could do our calculator, but this is root 2 over 2. And if you remember a little bit about sine functions, they're odd. So an odd function means f of x is the same as negative of f of negative x. So if you have a negative angle, you could replace it with the positive angle of 45 degrees and put the negative out in front. And that negative out in front with that negative make a plus. And then we've got plus root 2 over 2 again. And so you've got two of them added together. And so together that's just root 2. So now I can get this magnitude, and I'll save myself a little calculator work by crossing out the 4 pi. So this is 1 times 10 to the negative 7 here, then times the 10, then divided by the 0.2 would be this stuff in front. Then this sine of 45 stuff I determined was nothing more than the square root of 2. And so it looks like I've got a 7.07 times 10 to the negative 6 Teslas for the magnetic field. And let me emphasize, that is just from wire number 1.
Okay.
All right.
Would it just be 4 times that though?
Yeah. And so with a little bit of thought, good, you'll see that wire 2 is the same distance, the same configuration. You could probably even see it by just turning the square this way. Wire number 3, you can see it that way. You sort of turn it here. And wire number 4. So my final step would do say the total field would be 4 times the field I get from number 1. So times 4 gives me 2.83 times 10 to the minus 5 Tesla, which probably would be best written as 10 to the minus 6, which is micro Tesla. And then, of course, remember we said earlier on that the direction was inward. And so all of this would be the magnetic field from this square. And I'll switch over to the solutions here and see what they get for number 3. 28.3 going into the paper. Good. Now there is a part B to this. Part B says, okay, it says, what if you took this conductor and you formed it into a circle, now a single circular that carries the same current? What would be its value? Okay, so let me do this. Let me first draw a picture. And let's start with direction like we did before, but I'm going to put a little arrowhead and say, okay, here's the current. I'm going to make the current go in the same direction. Did they say same direction? Carries the same current and still clockwise. They didn't really say. But this 10 amps, they did make it clear. And let me use this as a chance to kind of emphasize that right-hand rule again. So if I take my second right-hand rule, if I take my right hand and I hold it in kind of the thumbs up position, and I look at my current is in a loop. So in this case, I would use my fingers to represent the current and my thumb for the field. And to make my fingers kind of loop in the same direction as this loop that I've drawn, I'm going to have to turn it so my wrist and my thumb is pointing down. So it would be something like this. And so now my pinky is kind of making a loop that is in a clockwise direction. Anyways, my thumb is pointing down, and so not a surprise that I would get a magnetic field going inward, or what you might say the minus k-hat direction. You're always going to get that when you're the inside of something going clockwise. So whether you're on the inside of a square or the inside of a circle, it's almost doing the same thing. Of course, your distances away are different, so I do expect the magnitude to be different, but not the direction. So sure enough, using the little right-hand rule, the second right-hand rule, I get into the board. Now, let me put a second very useful equation. And Ooh, I should check the OpenStax. I think the author did this one. I'm pretty sure in the OpenStax. But this is the analogy to this long straight wire. So if you ever have a long straight wire, you don't need to go back to BIPs of art and do the integration because this is what you get. But we also did this integration for a loop, and this is what we get. And just to highlight it, the A is the radius of the loop. The X is the distance along the axis of symmetry of the loop. The I, of course, is the current in the loop. And you might say that's just the magnitude of it, and we can get the direction using our right-hand rule. Okay. So for us, in our problem, since they're talking about the center of it, the X would equal 0. And so this equation significantly simplifies when you set X equal to 0. Page 2. So if I go back to this equation and set X equals to 0, I would get the magnitude of it as mu naught I. Let me leave the A alone here because watch this. X is equal to 0, that goes away. I have A squared, but this is taking the square root, so that's just A, and that's A cubed, but I got an A squared up there, and so ultimately I'm just left with one single A downstairs. So this is the equation for a loop, a single loop, with A being the radius and I being the current. Now, to answer the question, I think I need to know what the radius is. So when I make it this loop, the circumference would be 2 pi A. That's going to be the circumference. And if I come back to the wire they gave me, the wire they gave me was in the form of a square that had a length of 0.4. So the total length of the wire is 4 times 0.4. So this would give me information to figure out what is the radius that I can make out of this. So 4 times 0.4, that's the perimeter of the square. And then I'm going to set that equal to the circumference of the circle. So when I divide that by 2 and divide that by pi, I get a radius of 0.255 meters. And so now if I put that in here, this would be 4 pi times 10 to the negative 7. This would be a current of 10 amps. This would be a 2, and this would be the radius. So putting those into my calculator here, I would have the 4 times pi times 1 times 10 to the negative 7 across the top, then times the 10, and divide by the 2, and then divide by my last answer, and I get a 2.47 times 10 to the negative 5 Tesla, which I suppose I could write as 24.7. And that would make it 10 to the minus 6, which I will write as a micro Tesla. So 24.7 micro Teslas would be the answer for B, I hope. And let me come back here to the solution. Yeah, good. So, yay. We got it. So there's a good one for you.
Thank you for explaining the right-hand rule more. I was a little bit confused on that, but that helped a lot.
Good. Yeah, I got to keep saying that because I know that it's got to be a lot harder learning in this remote setting than even face to face. But face to face, I'm constantly saying that almost every day as I'm just kind of hanging out as students come in and saying, hey, you got any questions? And I'm like, yeah, wait. And even in class, and I hope it's in the video that, I pause and say, wait, don't, I say right-hand rule, but remember there's two of them. So let's call this the second or the third or the fourth, depending how you want to number the right-hand rule. Okay, well, with that in mind, I think we're back to Gino, number 17, right?
Yeah, number 18, please.
30, and so the time is 1:37.
Oh, 17.
17 or 18?
Please.
All right, I think I heard 17 final answer.
Yeah, I need to see all of them, honestly, so.
Oh, okay. All right. But yeah, I think what you're saying here is that if you see one, maybe two, maybe three, maybe four, hopefully you get to the point that, okay, I didn't think I could do number 18, but now maybe I think I can, and you can give it a try. That's the idea. But hopefully I didn't scare you guys, but encouraged you on the week's assignment that I said, hey, this chapter is the harder of the four, and you really want to work on it this week. And so it's glad to see you guys are all working on it, because you need 2 weeks for it to sink in. This first week is going to seem like I'm not getting it, and then next week you'll start going, okay, I'm getting it now. And hopefully by the weekend you're like, okay, I got this. Now I can review for the test. So that's the plan anyway.
Sorry to interrupt. Speaking of review for the test, do you mind if I interject with a quick question?
Sure.
Just about the test, not about a number.
Yeah.
You mentioned in the recorded video that we're not covering section 30.5 with the Gaussian surfaces of magnetism.
Yeah.
Is that still the case for the online, for this semester as well?
Yes, but also let me clarify. We are going to do Gauss's law of magnetism. We are going to do the flux of magnetism, but I'm going to treat that as part of chapter 31. So it's not on the test.
Okay, perfect.
Yeah, so yeah, you don't need to, and I'll try to make that clear when I send out, Sunday night, when I send out the assignments for the week, because this assignment this week is going to focus on getting ready for the test. And so part of that is, okay, well, what does the test cover? And so I will say it would be 27, chapter 28, chapter 29. And then in chapter 30, it's really only going to cover sections 1 through 4. And so,
Okay, perfect. Thank you so much. That's what I was hoping to hear.
Yeah. So that's hard enough. But if I was writing the textbook, I would have left the flux, magnetic flux, to the next chapter, because you don't do anything with magnetic flux until you get to Faraday's law in the next chapter. So we can learn about flux in this chapter, but it just leaves the students with a question. Well, why do I care about the magnetic flux? I mean, I got why I cared about the magnetic or the electrical flux, because Gauss's law, that helped me find the electric field. But the way he presents it, without Faraday's law, there really is no value in working with the flux until you see Faraday's law. So that's kind of my thinking, that, if we're gonna do these hard calculations with flux, let's also give the students a reason why we care about the flux, and that's Faraday's law. So it makes the chapter 31, a little longer than it is. However, another reason I think it's good to put it in chapter 31 is 31 is the shortest chapter of the whole book. By the way, notice I didn't say easy chapter, but it is definitely the shortest chapter of the whole book. Just Faraday's law and Lenz's law, and boom, you're done. But it's not easy. And so putting flux into that, I think it would be a better written book that way. But anyways, it doesn't matter. So that's the way I broke down the test, because I think we've got some really hard stuff and enough really to have an exam on, and to put this in 31 just makes a whole lot more sense. All right.
Awesome,
So,
perfect. Thank you so much.
Yeah, thanks for asking that. All right, so now let's go to, let's see, it was number 17. So chapter 30, number 17 and or 18, but let's do 17 before we can get, and then we have a 121 chapter here. I need to go back to the question. Okay, whoops, didn't want to do that. Okay, here it is. So 17 says this: in the figure, the current in the long wire has 5 amps. Okay, so they've got this long wire. They don't kind of show the beginning or the end of it. They call it current number 1. They say it is 5 amps. And it lies in the plane of a rectangular loop. And so to the side of this long current is a rectangular loop, which they say it has the dimensions of L and A, and is a distance of C away. At least the left-hand edge of the rectangle is a distance of C from the long wire. They say that there is a current in this rectangular loop. It looks like it would go around in a clockwise direction. And so they call that current number 2. And they say this lies in the same plane. It carries a current of 10 amps. Okay, so I2 is 10 amps. And the dimensions are 0.1 meters for its length. No, I can't read that very well, but I think that's a C. So this is 0.1 meters for C. A is 0.15 meters, and L is 0.45 meters. I got to really make some better copies for you guys. Now that I got, especially got the PDF, I can just electronically cut and paste instead of old-fashioned cut and paste. All right, find the magnitude and the direction of the net force exerted on the loop by the magnetic field that is created from the wire. Okay, so a big piece of this is to really go back to chapter 29, where the total force on a wire is the summation or the integral of a lot of little forces. And a lot of little forces come from a current, a little section of current. So I times this little section of wire crossed with the magnetic field. So if I was trying to find the force on this rectangular loop, I would essentially be doing this integral around the rectangular loop. I'm trying to find little chunks of force on each of these. And so why don't I just kind of look at this rectangular loop as 4 pieces. This I'll call wire 1. Then across the top, let's call this wire 2. Then going down, let's call that wire 3. And then this is wire 4. So what I would say then for the total force would be an integral, and I'm just going to put a number 1 underneath it. Another integral for wire number 2. Another integral for wire number 3. And another integral for wire number 4. So I'm trying to find the total force on this rectangle. All right. Let me start with number 1. Now, number 1 would look like this. It would be the current, and here's where I got to be careful. Which current? Are we talking about current 1 or current 2? Well, it would be current 2, because this is saying the current in wire number 2 coming from the field from number 1. So this would be a DS cross a B. And so maybe I'll put number 1 here, because the field is coming from current number 1, and that field is then putting a force on current number 2. So that's the integral I have to do. But I thought I might pause before doing the integral and look at the direction. And if I do the direction, this is a cross product. And so I call this right-hand rule number 1. Put your fingers in the direction of the current. So let me look at a little section of this current, maybe right here. And so I'll put my fingers in the direction. And then I got to close my palm towards the direction of the magnetic field. Okay, now where does the magnetic field come from? It comes from wire number 1. So what direction is the magnetic field from wire number 1 at this location of wire number 2? Well, that's where the second right-hand rule comes into play. This is where the 2 right-hand rules I was just going through with Daniel is that, all right, let's do this. Let's use the second right-hand rule. This is the one where you start with your right hand in the thumbs up position. You don't do any of this movement of the fingers, no cross product. Okay? You just hold it in this position. And so if I look at the current from wire number 1, it's straight. So my thumb is going to represent the current. And so if I hold my thumb right over that wire, my fingers in my right hand are looping around. So over here, it would be coming out. Now, we don't really care about that, but I'll just draw it here for completeness. I'll put a circle with a dot. The field's coming out. The field's going to loop around and go in right there. So that tells me the direction of the field from wire number 1 at wire number 2. So right-hand rule number 2 was important here. So let's go back to what I was doing here. Let's use right-hand rule number 1. That is, I put my fingers in the direction of the current, okay, here. I adjust my wrists so my fingers can close towards the field, which we just decided was down. And so what I would get is a force. I'll do the force in blue. But the force then on wire number 2. Ooh, I just realized my numbering's kind of weird. This is the first section of wire number 2. Maybe I should stop calling it this one number 1. I'm just going to call this the straight wire from here out. Okay, so the field from the straight wire, the long straight wire, is down. And so that makes a force on this first segment of this rectangular loop, this first segment of going towards the wire. So I want to just pause and say, you should just commit that to memory. This whole process that I just went through was done in section 2 of both textbooks, where if you have 2 wires and you have current in the same direction, they pull together. Before the break, we did a bundle of wires, and we had to find the force on one wire that was in this bundle of 100 wires. And since all the current was going in the same direction, we argued that they would pull together. And that's, I'm really saying the same thing. There's nothing different here. It's the same physics. So anytime you have currents going in the same direction, they pull together. And anytime they are in opposite directions, they push apart, which makes me think that I should probably label that for wire number 3. And maybe I should call it the third section of the rectangular loop, so I don't confuse you with my numbering system. All right, so the third section of this rectangular loop, this current here is opposite of the long straight wire, so it would push away. And we could even show that again. I will. Let me start with the second right-hand rule to ask, what direction is the magnetic field at this point of wire number 3 or section number 3 in the rectangular coming from this long straight one? So if I go back and use my right-hand rule number 2 and I point my finger in the direction of the current, I would see that the field comes out over here, as we already said, and on this side goes in. And so that means also it goes in right here. And so if I were to do a cross product of the first right-hand rule would give me the direction of a cross product. So I would take my right hand and I put it this way because now my fingers need to go in the direction of the field and I would close it downward, because I'm sorry, my fingers would go in the direction of the current and my fingers then would close downward, which is the direction of the magnetic field, and my thumb is pointing out. And so this would give me a force away. So simply put, wire number 1 is being attracted, or section number 1 of the rectangular loop is being attracted to the long wire, and section number 3 of the rectangle is being pushed away. So if they're equal, the net force would be 0, but if one is stronger than the other, then we're going to get a net force. And I have yet to prove it to you, but you can probably imagine that given that the first section is a little closer to the long wire, that perhaps the field is stronger here than it is. So therefore the force is stronger, and this is going to leave a net force pulling towards the long wire, and sure enough it will. Of course, that doesn't say anything yet about the top part or the bottom part of the rectangle. But let's look at their direction, starting with the fact that right-hand rule number 2 would say the magnetic field goes into the paper at this point, and over here at number 4, it goes into the paper. So if I bothered to do a direction, I would have to, I don't know if I can get my right hand that way, maybe I'll turn the paper a little bit, but I put my fingers in the direction of the current, close my hand down, and my thumb would point up. And so this second section would be pushed up. And if I do the same thing for the section number 4, I'd put my fingers in the direction of the current and close downward towards the field, and my thumb would point down. So section 2 gets pushed up and section 4 gets pushed down. And again, we could say the same thing. If those two are the same, then we would get a net force of 0. But if one is bigger than the other, then it would go in that direction. I think you can see that even if the field gets weaker as we move away from the long wire, this section and this section, I would call them symmetric twins. That is, they are in the part where the field is stronger compared to over here, but they are both in a place where it's strong. And so this little section is pushed up and this little section is pushed down by the same amount. So the net force of those two are 0. And then over here on this end, the force would be smaller up, but also smaller down. Those two would be 0. This is a long way of saying that I'm not going to even mess with trying to figure out the amount of force on wire 2 or wire 4. I know that they are equal and opposite. It would be, again, taking this integral, and of course, maybe you remember from your math class, if you integrate from a to b of some function, that is equal to the negative of b to a of that same function. And that's essentially what I'm doing here. I would be doing an integral along, left to right along the current for number 2. Maybe I'll even write that down. This would be from, this point here, let's call it C, to this point here, which would be C plus A. But then this one down here would be an integral from C plus A to C. So those two are going to be equal and opposite. So that's really, I think, important to notice, because although I haven't gotten there yet, the field does change, and that would make a hard integral. And not too hard. It comes out to be a natural log integration. But this, then, I don't have to mess with. All right. So that's really reduced this to much, much easier problem. I only have to worry about, on the rectangular loop, I only have to worry about wire number 1 and wire number 3. Oh, by the way, I hope you notice, so far I'd say I'm doing really a lot of physics, really very little math. I'm doing, of course, trying to understand directions with the right-hand rules. But it looks like at this point, I would say that I can make this problem much simpler on myself, realizing that 2 and 4 are going to cancel off. I don't need to mess with them. And then 1 and 3 are going to be almost identical, but 1 is going to be a little stronger than 3 because we're a little closer. So let me use this as an opportunity to then say that we've learned, and it's worth committing it to memory, and I can go back and kind of show you if you want. Your author does it with B. Sub Art, and then he does it again with Ampere's law. What is the magnetic field from this long wire? So I've been just talking about that there will be one, but I haven't really said what the equation is. And this is the equation. So I've been doing direction, but this is the equation. And so notice the equation says it depends how far away you are. And that's what I was saying. That's why the field created for the first section 1 of this rectangular loop would be a stronger field than the one created over there. But here's what makes this integral very simple to do, is that when I then put this integral down here, here's current number 2, and I do this cross product, it would be the magnitude of the ds, the magnitude of the field, and then the sine of the angle between them. And as we already said, the current is going up and the field is going down, so that would be 90 degrees. And of course, the neat thing about sine of 90 degrees is it's 1. And so not only is it, 90 degrees, it doesn't change along this whole integration. And likewise, the value of B right here, given by this formula, is always a distance of C away. So this doesn't change. So in other words, when it comes to actually doing this integral, current number 2 does not change along this first segment, and the magnetic field along this first segment does not change. And so all I have is an integral of ds. And I would say that's not even doing an integral. That's just reading an integral. That's just saying, hey, this is just saying add up a bunch of ds's. Just add up the length from here to here. Well, that's the L. And so this is just L. That is what that integral means, add up the length. So what looked like was going to be a hard problem with these 4 integrals, actually, after a little thinking, realized I don't have to do the harder integrals of 2 and 4. They cancel off. And the integral of 1 is so simple. And so this would just be the current in number 2. The magnetic field coming from wire number 1 would then be this equation, mu naught times current number 1, all over 2 pi. And then the r is the distance away, which is C. So there's the magnetic field, and then times L. So this is the integral here of this first one. This is what I would call force from wire number 1. And hopefully, to make this understandable, number 3 would be identical. Force number 3, bring this back into view. Force number 3, I would be doing this same crazy integral. It would be this cross product, and I didn't write it out here, but it would look just like this, where it would come out and I would do this cross product and I'd still get 90 degrees. Now, granted, the current's going down, but the field is inward, and so that's still 90 degrees. And so the same thing can be said, that that's nice because it's always 90 degrees, and that just comes a 1. And then the magnetic field would be, again, a constant everywhere along, hold it down this way, along wire number 3. So that's going to be a constant value. And the bottom line is we're going to end up with the same thing. Although when I go to put it in here, I would put current 2, and I would put mu naught times current 1. But now I would say that my distance away is C plus A. And so that's kind of the difference. It's still a length L. And so that would be the magnitude of number 3. So finally, I can get to answering the question, what is the total? Because number 1 would be then to the left, and number 2 would be to the right. If you go ahead and let me call the right the negative direction. And so I would have number 1 here, which I'm going to write then as current 2 mu naught I1 times L over 2 pi C, and then minus I2 mu naught I1 L all over 2 pi, and then what did we say it would be? C plus A. So maybe I'll just factor like terms out here for a moment. And then I have a 1 over C minus a 1 over C plus A. And so now I can actually put in my numbers. Okay, so current number 2, what I said, 10 amps, so 10 times, now I'm going to save myself a little calculator work. This is 4 pi times 10 to the minus 7. So canceling that off cancels the pi's, and the 4 goes down to a 2. And then I don't have anything downstairs. So I'm going to write that as 2 times 10 to the negative 7. Then times the current number 1, which we said was 5. And then the length of this is 0.45. Okay, so this is 4.5 times 10 to the negative 6. Now this would be C, or the reciprocal of C. So let me go 0.1 reciprocal. Maybe I better just write it as 1 divided by 0.1. Minus then 1 divided by, now I have to add the 2 together. I can just do that in my head. That's 0.25 and hit enter. So that's a 6. So then I can take my 6 and multiply it by that number up there. Let me grab it and paste it in. And I get 2.7 times 10 to the negative 5 newtons. Maybe I'll write it as 27, because then that becomes 10 to the minus 6. The micronewtons would be the net force on this rectangle. And if I jump over to 17 on the solutions, they got 2.7 times 10 to the minus 5 newtons towards the left. Yay, good. Now, I hope I didn't do too much, because I will tell you that the author had already worked out this equation. So I see in the solution, the author just jumped right on the equation he already worked out. So feel free to do that. You don't have to come back and talk about these integrals. But I think you do have to justify that 2 and 4 cancel off. And he justifies it in words, but it's nice to see it in integrals and the calculus and in the reverse fashion.
Thank you so much. That makes a lot more sense to me.
I hope so. And you and everybody else out there, don't feel bad if it doesn't completely make sense. Watch this many times. In fact, I was thinking about you guys last night, and I kind of read the questions. I thought, oh, they're going to have some really tough questions here today. This is hard stuff. And I knew it was. That's why I decided to read them ahead of time. Sometimes I can just read them on the fly, but I was reading them. And then I got lost just wasting time and surfing YouTube, and I came across a great, one of the channels I like is called Real Engineering, and it just shows how designed. And they had an Allison transmission, and they were showing how you get the 6-speed and the reverse and a planetary gear system. And I go, you know, I don't know really how they do that. I'm curious. So I watched the video about 10 minutes, and I got done with it, and I go, you know what? I think I only understood about 20% of that. I better watch that again. And literally, I watched it a second time, and I still didn't understand. I watched it a third time, and I was like, okay, I got first, second, and fourth gear. Fourth gear was actually real easy. It's a direct drive. But I could not figure out how they were getting overdrive out of it. So I thought, what? So I watched it a third or even a fourth time, maybe even a fifth time, and finally I got it. So what was a 10-minute video turned into an hour, and I finally got it. So I'm trying to say is, I get it. You're not going to get it the first time. Don't expect to get it the first time, but you got to work on it now because you got to watch these 5 or 6 times before they sink in. So I'm glad we're recording these, but that's what it takes for some of all these right-hand rule stuff.
Professor, did you happen to say that a couple of the problems in chapter 30 came from sections 5 or 6?
They did, and I'm glad you say that, because I should also put that in my Sunday announcement of the assignments, because I don't think any of them were on the first page, which I'll call the first page, the page that was missing that we just did and I sent you. But let me scroll down here to page 2 of chapter 30. And yeah, there's some hard ones on here. Yeah, but okay, so chapter 30, page 2, number 39 talks about flux. So that is not necessary to do. Then they call, there's some, but the next 2, 43 and 45. I'm even to write this down so I can remind myself when I put it on Sunday's announcement. 39, 43, and 45. I don't want to encourage you not to do them. They're great problems. But again, 39 is more about flux, and 43 and 45 are really good problems. It's just, this is the borderline between doing magnetism in free space and magnetism with materials. And that's really kind of the opening for your second class on magnetism. And so I'm glad your author has a section on it, and I kind of want to cover it, but I don't want you to get overwhelmed and feel like you have to know that, because that's what the next semester is, or I should say next year, because you guys are probably going to transfer the next fall. And so not completely knowing that is fine, which is why then 65 and 66 kind of fit into that category too. They're a little more exercise on calculus. But those would be the 3, I would say, 39, 43, and 45. If you struggle on those or don't even want to look at them because you're still trying to get it all done, those are the ones to skip.
So if we didn't have those 5 problems when we turn in homework, would we get marked down for that?
Oh, no. Oh, no. Yeah, no, I'll say no. That's cool.
Okay.
Yeah, that's cool. You guys got some tough stuff, so just get ready for the exam. I mean, like I said, anything you do for the next chapter and anything you do on these problems because they're related to the next chapter is great. But, especially with this hard chapter right at the end, it's like, okay, why don't we, just make sure we're ready for the test, and we'll worry about this stuff after the test.
That's really good to know. Thank you.
Yeah. Good.
Are we gonna be doing chapter 31 next week, or are we just gonna be getting ready for the test?
I'm going to put out there, like I did last time, that if you're not completely ready for the test, don't start working into 31. You know, get yourself ready. That's the priority number one. However, if you have the time or you're burnt out on working at that and you just need to look at something different and something that is non-pressure and something that'll actually help you learn chapter 30, because as you try to do 31, you do have to kind of understand 30. So it does help you in a way. And so I would say that's the way to maybe keep working forward so you don't get overwhelmed after the test. But certainly if you're not ready for the test, don't worry about that. Sometimes you just got to do what you got to do at that moment, you know.
Okay.
Yeah.
Would you say the best way to study for the test is just like get caught up on all the homeworks and then just work through different homework problems not assigned?
Yes. Definitely work through all the homework first, and then definitely, try problems that weren't assigned at random. They really tell you how you've done. Now I see we're over time, but I'm not worried about that. I wanted to get these 4 done, and so Rylan, that's what it is, Rylan. I don't see you in. Am I missing anything? I don't. There are more pages? No.
I don't
Maybe
see Rylan either.
Yeah, it looks like he cut out. Bummer. I hope I didn't talk so much. I lost him. I hope he'll come back. But maybe just as well. I wanted to do that one before we went to a break, but why don't we do our break now? And I will even write down Taylor. Looks like he's gone. He's got number 36 from chapter 30. Here's a 27 from chapter 30.
Oh,
All right. Oh, here's where he writes. I got my 21 question answered just now. It was about the quiz. Thank you. Maybe it was the same one on the quiz. I don't know, or somebody else helped him, or he figured it out. Oh, then Gina writes, I did number 27 and 30. Oh, I did those, huh? Okay. Yeah, I was wondering if I did. Let me look back on section 1. Well, when we come back from the break, if Chase, are you there? No, you're not there. You want me to do 30 or Tyler? Well, maybe they left after they heard they did it and they're waiting for the recording. But anyway, if they're back, I'll do them. But you're right, Gina, I would prefer to do something new and direct them to the recording when I get it published tonight. So if there's not new ones, I'll redo those ones. But let's do new ones first. And then number 18, that was also your question, Gina, but this is from Anthony. Okay, so let's do that when we come back. Let's do number 18 if you're around, Anthony and Gina. Hopefully you'll be around.
Yeah, I can. 3 o'clock.
Okay.
Or is it 2:30? What time is it?
Let's see. What do we supposed to stop at 2 and break till 3? So yeah, so 3 o'clock. So we'll be back in 45 minutes.
Okay.
Okay, then.
Right.
Cool.
See you soon.
Thanks.
Okay. Well, bye now, guys.